Hi folks, we're going to take a look at number 11 on page 179. So they give us this quadratic function and we've got two of the coefficients are unknown. Okay, and they tell us that f at 1 is equal to 5, and they also tell us that this is an extremum of f. Okay, so we know that we look for extrema at critical points, which are points where either the derivative is equal to 0 or does not exist. But since this is a quadratic and so the derivative will be linear, we know that there won't be any points where the derivative doesn't exist. So we can conclude that f prime at 1 has to be equal to 0. Okay, and these are the two pieces of information that we're going to need to solve for the two unknowns. Okay, so I have to choose which piece of information to input first. But I think a trick you've seen a few times now is that I'm actually going to work with the derivative first, because when I take the derivative of this function, the q is going to disappear since it's just a constant, so leaving me only the p to solve for. Okay, so I'll start by finding the derivative here. So f prime at x is equal to 2x plus p. Okay, and now I'm going to evaluate the derivative at 1, and that's got to be equal to 0. So the derivative is going to be equal to 0 when I evaluate it at x equals 1. And so that's actually a pretty easy equation, and I determine that p has to be equal to -2. Okay, so now I'll use the other piece of information to determine q. Okay, so I know that f at 1 is equal to 5, so the function value is equal to 5 when I replace x by 1. I already know that p is equal to -2, so -2 times 1, okay, plus q. Okay, so here we're left with 5, so here we've got 1 minus 2, -1 plus q, and so q is just equal to 6. Okay, so now we've determined the function. Okay, but what they want us to show is what type of extremum we have at x equals 1, whether it's a minimum or a maximum. Now, we should already know that because this is a quadratic with a positive leading coefficient, we know it's going to be a minimum. But let's use our first derivative test to determine that. Okay, so we've already done the first part. We have our critical point. That is where the derivative is equal to 0. So we just have to test to see if there's a change in sign in the derivative. Okay, so the derivative function now is just, well, 2x plus p, so 2x minus 2, because p was equal to -2. Okay, and now I'm going to use that little number line representation here. So my critical point is at 1, and so this function here, which crosses 0 at 1, since it's a line with a positive slope, I know it's going to be an increasing function. So that means that the derivative goes from negative to positive when it crosses x equals 1. That means that the function goes from decreasing, okay, where the derivative is negative, to increasing where the derivative is positive. So that means that we have a minimum. Okay, so we have a minimum at 1, 5. Okay, so just to recap here, okay, we'll see quite a few of these problems where we're working with some function that have some unknown coefficients. Okay, consider whether it's worth working with the function first or the derivative first. In this case here with a polynomial, it was better to work with the derivative first. Okay, and then when you're applying the first derivative test, be sure that you're not just determining where the derivative is 0, but there has to be an actual change in sign. Okay, and if the derivative goes from negative to positive, you've got a minimum. If it were to go from positive to negative, you'd have a maximum. Okay, that's it for this one.